Good morning, everybody. This is our third day. DecisionCAMP is going well, but we did have a small change in our schedule, and our first presenter will be Meinolf Sellmann, and Meinolf is expert in optimization, in particular in stochastic optimizations, and he has both academic and industry background, and this experience allowed him to create a brand new solver that does not look like any other solvers available in the industry, called Seeker. And last year he presented a very interesting use of his solver, and I still remember your quote about when you compared decision modeling with play by Roger Federer. And I expect similar and even more interesting thoughts you will share today. Meinolf, thank you very much for being here. Go ahead.
Thanks so much for having me, Jacob. All right, so I'm going to talk about one of the biggest strawman that's being made out against stochastic optimization. That is, well, where are the distributions going to come from? Right, so how do we estimate the likelihood of particular scenarios, which it sounds like you're gonna need for stochastic optimization? We're gonna dive into that. So I'm gonna start exactly the same way as I started last year, and talk about the promise of optimization, right? So since we're starting a new topic here on decisioning, if you think about it, the reason why you have a brain, why evolution favored individuals that have a brain, is for one reason and one reason only. It's not because they had beautiful worldviews or world models or that they could forecast things, or so they were making better decisions. That is why brains, why intelligence at a huge cost to the individual was an evolutionary advantage. You do, and it's, if you work in this area where you're using computers to make plans, you have a very noble profession. You make more with less. That implicitly means more sustainability. See, the best miles are not miles that are driven with an electric car, they are miles that are never driven. The best materials are the ones that you don't need to waste at all. We can increase competitiveness. We turn forecasts into value, and we bring efficiency to the world. That is, at the end of the day, what we're doing. And we have standard core technology that we've been using for, well, in earnest since the late 70s, early 80s, and that's mixed integer programming. But the world is bigger. So there is that part that you can solve with mixed integer programming solvers, but then there are problems for which you could still kind of use the same approach, which is, well, you use bounds to remove areas of the vast space of potential plans that you could follow, and to eliminate them. So there are problems for which that works, where you have a reasonable bound that you can say, oh, I already have a plan that's better than all of this stuff. I don't have to look there. They are the so-called relaxed fit problems here. The most real-world problems, you're really not going after this one objective. You usually have to juggle a couple of KPIs, and sure, you can constrain some and optimize the others, but think about buying a house, for example. It's not like you say, well, I really, really have to have 3 bedrooms, and you wouldn't be unhappy if you had 4. Right? It is a better house if it has 4. So the moment that you just constrain one of these KPIs and says, well, I'm only going to look at houses that have at least 3 bedrooms, while that's correct, a house that has 4 bedrooms is better. So if you want a computer to search for an optimal house for you, it needs to understand that 4 is better than 3. But of course, you also have price, you have school district, you have distance from work, and all of the other considerations that go in there. So typical real-world applications are multi-objective. And then, of course, most of the data that goes into your models is estimated. And we'll go over that in a second. And then, of course, most of the problems that we're dealing with are non-convex and non-differentiable. So we have technology, the MIP technology here in the lower right, and that is good for what it's good for. But there is a world of other problems out there for which we don't really have technology if we limit ourselves to mixed integer programming. So here's a reality check on stochasticity, right? If you study this area in operational research, right? So if you go to a business department, you might find an operational research department in there, and they will teach you problems like facility location, right? So it's network design. Where am I going to put my distribution centers given transportation costs, transportation times, and demands? But in reality, these locations are not predetermined, right? So the standard MIP models assume that you already have candidate locations where you can put your distribution centers. In reality, you can put them anywhere. Think traveling salesperson, right? So the classical problem of just finding a permutation and ordering of looking at nodes in a graph. In reality, we don't really know how long it's going to take our technician to do the work at the node and how long it's going to take them to go from point A to point B. This is all estimated. Pricing is typically nonlinear. And of course, we estimate the price sensitivity. How much demand you're going to get at a certain price is an estimate. It is not set in stone. Production planning. It's non-convex. We have estimated demands. We have estimated scrap rates. Inventory relocation. Jesus, yes, it's multi-objective, right? There is the fill rate that you want to maximize. There's the inventory cost that you want to minimize. You want to minimize the overhead for the orders that you're having. You also have to take into account that there's a loading dock that has to take all of this stuff into account. So it's very multi-objective. And of course, if we knew exactly what was going to be bought, we'd know how much to order. But in reality, we neither know that, nor do we actually know how long it's going to take our suppliers to supply us. Right? So when do you have to order? You have to take into account that the order might come in late. So most of these problems are actually stochastic, multi-objective, and nonlinear. And single objective, linear deterministic optimization is a rare exception, even though OR makes it sound like it was the default and the is-all, end-all of all optimization. Not true at all. So this is where I left you off last time. What do we actually put instead of it? So we came up with an approach that doesn't work based on bounds, but that works based on AI. And it's a primal method, so it means it starts off with a plan and tries to improve it. And it uses AI to learn how to improve your plans. Hyperparameterized, which means that if you have a set of problem instances that you want your solver to work better on, you can just shove it into an automatic tool and it will improve the parameters that guide the search inside the solver. It's automatically configurable in that way. It's fully distributed. So it's another huge advantage that you're getting if you go primal, that you can suddenly use 2000 cores if you can afford to solve a problem. It's not something you can do with MIP. After 8, it's a bad idea to add more cores. It's multi-objective, it's stochastic, it's non-convex and non-differentiable. So let's look at an example and let's burn that straw man of, well, you really need accurate probabilities in order to do optimization in a stochastic fashion. So what do we have here? We have a hospital. And in the hospital, there are 3 surgery wings. So you have these OPs here. So each of those surgery wings has 3 OPs, right? So the operating rooms, and 4 PACUs. I apologize that this is called PACU and not PACU, but I was tired of generating images with Gemini, so I took it for what it was. A PACU is a patient recovery unit, right? So after anesthesia, you cannot just tell the patient, okay, here, slap, left cheek, right cheek, get up and get out. They have to stay with somebody who actually looks after them. It's much like an ICU where you're staying, where somebody looks after you in case that there will be problems as you're recovering from surgery. So what you have here is you have a bunch of operations that need to go into each of these wings, and you have to schedule them. You have to say, well, okay, this patient will go at that time, and we'll have them on that day, and you're 5th in line or something like this, and then afterwards you have to go to a PACU. Now these recovery times can be long; they can vary a lot. So can the OPs, the operations. So the question becomes, well, where do you actually put people? Well, the hospital isn't stupid. They're going to use for the next patient the first available operating room, and they're going to use the first available PACU that is there. If there is no PACU, meaning all the PACUs are full and you're done with your operation and the patient needs one, your operating room will become the PACU. Meaning you're gonna stall all further surgeries that were scheduled for that operating room that day until that person can be moved to a PACU. Right? So there can be disruptions in the schedule if you're unable to move somebody out of the surgery room and into a PACU. Right, so we're going to look at just one of those wings because our hospital came to us and says, look, we're paying, just because of schedule disruptions, we're paying about $1 million a year, and we can't afford to do that anymore. Help us out of there. So what does it look like, right? So for the surgery room, we have 480 minutes of OPs per day, right? So these are our highly paid doctors, and regulations say that they can't go over. So what happens is that if you are in an operating room and you have the next patient that you're supposed to be taking care of now, and their designated time, right? So you have designated times for each operation and for the recovery for each of those surgeries that is there. If that designated time fits into the 480 minutes in the operating room, you're going to do the operation. And the PACUs just run. There is no cutoff time for the PACUs, right? So the nurses, we have enough of them, but the doctors are the problem. So you see here that this is the schedule, right? So on day one, we have a patient who needs an operation, and it's going to take 45 minutes to operate them. And then the designated PACU time is 180 minutes. And then there's another one, also 45 minutes, but PACU time is 170 minutes. And so on, right? So they can be the other way around too, right? So if you look at patient 15 on day one, the operation time is supposed to be 3 hours, but only half an hour PACU time. So you have all of these, and you need to schedule these patients on these days so that the doctors, that we're not going to bump patients to the next day. Because if we cannot schedule you, if your designated time in the operating room would go beyond the 480 minutes, we have to move you to the next day, right? That's the rule. And the bump costs us $3,500. We have to prep the patient again. We have an extra day in the hospital. It's costly for the hospital to be doing that. Problem is, I mean, this would be all good and well in MIP world if everything was deterministic. Right, so if all of these operations would take exactly 45 minutes and 180 minutes recovery, right, for patient 0, fine, right? We could just do this, but they're not. So what we are estimating here is that the true times, both for the operation and the recovery, run with a gamma 16 mu over 16, which essentially means it's almost normally distributed with 25% standard deviation. But the gamma makes sure that you're not going to run less than 0, right? So it's going to shift this a little bit to the right. All right, so that's what we have. Now, what you would traditionally do, in fact, what the hospital currently is doing is it uses deterministic optimization. And how would you do that? Well, you minimize the make span, right? This is kind of like, leave as much buffer on each day in each operating room so that you have room for things that go longer, right? That's the bottom line idea. And the solution they're starting from is, it's 1.75 bumps per week that they're seeing, and it costs them almost $1 million. Right? The schedule looks good. Right, if you look at them, and this is not stupid the way how they're packing on each day these operations. All the 3 operating rooms are roughly at the same time, and we are maximizing this buffer here that we're having, so that if things go wrong, there is room to breathe. All right. Okay, now we are trying to improve this, and we're going to improve it to this. We're going to bring it to almost 1/3 of the bumps and $330,000 a year for the bumps using this solution. And you go like, that looks exactly the same. It's like, what's different? Well, what's different is that this schedule here was made with a stochastic solver. And I'm quickly, right, because you might think, Jesus, that must have been complicated. I'm going to show you the entire program that produces this schedule. So what we do here is we build a Seeker environment. We use number of scenarios. I think I used 100,000 or so in this case, but I'm not entirely sure what it was. And now what I'm doing is for each day, I'm getting myself a permutation of the operations, right? That's what we're looking for. And that's it, right? So my decision is a permutation of the 16 operations that we have every day. So it's, 5 times 16 factorial, right? So, well, or 16 factorial to the 5, I don't know. Anyhow, we have 5 of those 16 permutations that we're looking at here. That's our search space. And now we are preparing the data. So we have the designated time that it would take. And what we do here is we put the gammas here on the recovery and on the operation times and make the whole thing indexable. So this is what this tensor means. It means, so if I make it a tensor, it means that a seeker affected variable can be used as the index to pick what the time actually is, right? Which we're obviously going to need. So then we initialize some values and then we go and simulate the week. That's all you do. So you get the actual you get the actual time here from the stochastic data for the OR time and the Pacu time. Then you're going to use the operating room as you're scheduling this. You're going to use the operating room that is the earliest that is available, and the same for the Pacu. Right? That's essentially what's happening over here. And now you have an end of the OP time. So this is a real end. It's the start of the operation plus whatever the real time of this was. And the designated end is, well, that's the plan. And we're going to use the designated end to decide whether we do the operation that day or not, right? So if the designated end is greater than the 480 minutes, then we have to bump this dude, right? Because we're not allowed to enter in an operation where the designated time would be going over the 480 minutes. If the last operation goes over, that's fine. I mean, the doctors are not just going to go like, okay, that's it. Let's go to the pub. They will finish the operation, right? So that's fine. Good. And right, so the rest is just bookkeeping in terms of what does this actually cost. And then the last thing we have to do is, well, if they were bumped on the if we bump somebody so this happens on day 1 to 4, right? So to Thursday, then we have to move them to the next day, right? And that's all that's happening over here. That is the whole program. That's it. And now you just tell the whole thing, okay, look, we're going to minimize some of the bumps, and we're gonna put a slightly little thing on here. So sometimes you have it. So you would have a big plateau here, right? So for many different plans, you would get the same number of bumps. And so what you want is you need to tell the solver when it's actually making progress. So what we're going to add to the objective function here is a little tilt where we're computing, well, how late were the bumps? So if you get them closer and closer, that's making progress to having one bump less. Right? So we're going to add that, but you see that we're discounting this with a huge factor of 10,000. This is really just a slight tilt of the billiard table so that our balls are moving towards the holes. That's essentially what we're doing. Otherwise, we have these big plateaus where essentially the solver would do a random search and a random walk. We don't want that. Okay, that's it. Right, so then we say, optimize this for the time limit, and right, you want to minimize that and get it out. Now this is the result, right? So we get a factor 3 improvement here. Instead of 1.75 bumps, we get 0.6 bumps, and it doesn't cost almost 950K, it costs 332K. So now back to what this talk is about, which is, yeah, Meinolf, but you're assuming it's a GAMP. Well, what if it isn't a gamma with which the durations of our operations and PACUs are changing? So what we're going to do for every last operation, right? So the 5 times 16 operations that we have, we're going to randomly pick whether we're now going to modify the length of that operation or the PACU time with a normal distribution or with an exponential distribution. So it's a random flip for each one of them. And we're also going to choose a new standard deviation for that distribution compared to the old one, right? So the old standard deviation was 25%. We're going to sample a new one. And we're also going to give it a new mean that we also sample. So meaning that our original gamma distribution that we had here for how the operation time should vary is turning into, for example, this blue dude, but it could also be this red dude. Completely different distribution, different mean, different standard deviation, different shape, right? Completely different for every last operation that we're having. And now we go, and from these new distributions, we sample 10,000 scenarios. And we do the whole thing 100 times. So meaning 100 times we're choosing a new distribution for each operation. And then we evaluate that scenario 100,000 times and compare how our solution works compared to the min-max-span solution. So it's always the same solution, right? So we assumed a gamma distribution, which was wrong. It was, none of them were gamma distribution. They were either normal or exponential now. We assumed a certain mean. We assumed a certain standard deviation. All wrong. But we got one solution, an ordering in which we're going to shove our patients into the operating. And we compare that to the min-max-span solution that we got from a deterministic solver. 10,000 times for each of these 100 scenarios. So you get 100 dots here, and over those 10,000 scenarios, we compute, well, what is the average number of bumps you're going to get? All right. So you see 100 things here, and each of those 100 is, well, we somehow sampled one way for certain operations and PACUs what they are, right? This is what each of these dots is. So what you see is the stochastic solution is never worse than the deterministic one. Never. That doesn't happen. You don't see anything under this first diagonal over here, right? The other thing that you see is, well, if you take the average of all of these here, that you're factor two better. Not quite the factor 3 that we were assuming when we thought, well, we got the right distribution. But it's still a factor 2 better than the than the deterministic solution that you get. So what does that mean? Well, if somebody is in love with optimization and provable optimality, well, naturally they're worried about getting the wrong distributions, the wrong probabilities to scenarios. Because if you have the wrong probabilities, how can you be provably optimal? So they choose something where they can do something that's provably optimal. This is the min-max-span solution for this problem. Unfortunately, it's also factor 2 worse than if you actually do it the right way and use the wrong distributions and optimize for that. Why? Well, because under the realities that you're in, where things deviate, and they always do deviate, you can be not optimal and still better. And that's the task. You need a more realistic way of representing your system, in this case, these operating wings, and get a reasonably good solution for that under stochasticity, so with robustness against lots and lots of different scenarios. And that is better than to have the provably optimal solution to a model that is further away from reality, which assumes that everything has a certain length and couldn't vary. That is what we're learning, right? So if somebody's obsessed with optimality, they have to make concessions on the models that they have to clip reality into. And those concessions are more costly in suboptimality than getting a suboptimal solution to a model that is more accurate. Even if the distributions are way off. And the reason why this is so robust, of course, is because if you're doing well against some cloud of scenarios that is around what might happen, you immediately gain robustness also if the likelihood is slightly different. Right? It doesn't make that much of a difference on how different these likelihoods are. You made sure that you're going to do well against these 100,000 scenarios. So if one of those scenarios had a different likelihood, well, okay, so what? Right, so what? It doesn't matter. I mean, you're already robust against this whole snowball, and that means you're also going to be robust against a slightly different shaped snowball. But where you're never gonna be is exactly in the mean scenario. It just never happens. All right, so promise of optimization, right? So it's a very noble thing. We do optimization in order to improve efficiency of the world. We have optimization technology to do all of this stuff, and now we are adding AI-based search to the mix in order to also tackle stochastic, nonlinear, and multi-objective optimization problems. So with that, I want to open to Q&A. Curious to hear what you think.
Okay, that's very interesting as usual, and let people to ask questions. Yes, Antonio, please.
Jacob, thank you very much for organizing this. It's definitely very interesting. Meinolf, really good to see you again. And definitely, I fully embrace the approach that you are here discussing, very much to my appeal. And of course, understand that, this type of approach is not exactly typically probably optimal, but it's showcasing that it's considering the uncertainty in a way, and in some way you're quantifying the uncertainty. My question to you is, surely you have carried out some analysis where you have played over the parameterization of the distributions that you're hypothesizing and such. Do you have some systematic way that you suggest that we do in those cases, specifically maybe the gamma distribution or maybe some other distribution where you can do MLE or 100 other approaches to parameterize the distributions with the same sample that you have used to compute the means, standard deviations, and so on?
Right. So I'm not 100% sure that. By the way, it's good to see you again, Antonio. We often connect on LinkedIn. So I'm not sure that I 100% understand the question. So what we did here was to say, okay, so I had an assumption when I built my stochastic solution, right? So I assumed that it was a gamma distribution. By the way, the fact that it doesn't look like a textbook gamma is because this is a KDE plot based off of the samples that we're using internally. But this is a gamma, this is a normal, and this is an exponential, what you're seeing here. And we're changing it, right? So we're saying, well, we built a solution where we assumed that each one of them was a gamma with 16 mu over 16. The solution is always the same for all 100 points and 10,000 evaluations per point. There are two solutions, there are two plans at work here. The min-make span and the one that we found where we assumed the Pacu times and the OR times were gamma 16 mu over 16.
Oh, fair.
Right.
I don't think my question was very clear. What I meant to ask better is, so you did some type of, to keep things simple, MLE type of approach to determine what are the parameters of the gamma distribution or something of the sort?
Oh, you mean how we actually came up with the 16?
Yes.
Yeah, but I mean, in this case here, we're assuming it comes from the client, right? So I mean, what you would do is you would look historically. Okay, we had our operations, and I mean, here we're simplifying this because this is out of a puzzle, and we just assumed it's 25% for all kinds of operations. In reality, for each type of operation, you would have some form of a distribution that you could do a KDE or whatever.
Yeah.
Yes.
Okay.
Yes.
That makes sense. Thank you.
Okay,
Absolutely.
Helmut.
Yeah.
Helmut has a question.
Yep. Hi, Meinolf. Very nice talk. I just had a similar question. Have you actually tried to fit the distribution on actual data to see what the distribution actually would look like in reality?
So, I mean, this is obviously what we normally do, right? So the point of this study here was to say, well, what if you come with one assumption and that assumption was wrong, right? So what happened? I mean, it could also be that, so for example, it could be that you have drift, right? So I mean, history is only an imperfect predictor of the future, even distributionally, right? There might be something else that all of a sudden, certain types of operations have a larger mean than they used to have. I don't know. Maybe the doctor who was really good at doing them is no longer with the hospital or something like this, right? So and everybody else now needs 10 minutes more. That is kind of why we go in here and we say, okay, so for this operation, maybe now actually the distribution is shifted in the mean. But of course, you're right. I mean, in practice, what you would do is you would build some form of a machine learning model that gives you a posterior distribution. If it doesn't give you a posterior distribution, you can always use your cross-validation or something like this. And then do a covariance analysis to get even a joint forecast for everything that happens in case that things weren't independent of one another. Here we're assuming that there's independence in the length of one operation to the other. But if you wanted to guess that from data, it's actually very simple. Even if you have a machine learning pipeline that estimates the mean right now, you can just look at the historical residuals, right? So the historical errors that you've been making, and just use them as training data in order to get a distribution on how, in reality, the training set deviated from what you were forecasting, right? So not the training set, the validation set, right? So that's why you're using cross-validation for that purpose. But yeah, I mean, obviously, in reality, you wouldn't just assume, well, it's gamma 16 over mu over 16. It's right. You would actually use a real distribution. The point here was to say, well, what if the actual distribution that hits us later looks completely different? Good question. It's good to see you again, Helmut. Been a while.
Okay. Good. Tim, you have question? No? Okay, we have more time for questions or comments. Yeah, while it's very impressive, you can see it's not a topic that everybody in this community really follow. And so experts still prevails, like Helmut or Antonio. And Antonio has another question or comment.
Given that there is time and there's only so many of us, Meinolf, what are your thoughts when you may have need for multivariate distributions and such? What additional complexities other than the obvious do you think we need to take into we need to consider?
So okay, so what Antonio is asking is, well, if you're estimating multiple pieces of your optimization model, right? So multiple data points, and they're somehow correlated with each other. They don't run independent of one another. What do we do then? And the answer in Seeker is very simple. You just shove joint scenarios into the solver. So what you can give the solver is not just, so in this case here, right? So if you look at the code, like when we put the stochasticity in there, you see here that I'm getting myself a gamma, and that is an environment variable. You can put your own distribution there if you have one, right? So you don't have to choose one of the standard distributions. We just added a bunch of more. I have terrible feedback right now. Okay, thank you. You don't have to use the normal, the Weibull and all of the other stuff that is in the solver. You can actually put your own scenarios in the solver. You just give it a way to sample scenarios. And what the solver allows you to do is that you sample joint scenarios. So you give me a whole vector, which is all the data points that affect your model that somehow move in unison in different scenarios that make sense. Okay, so you can provide the solver with your own distribution and also your joint distribution over multiple different data points. Now the question is, if you're in a business and you suddenly have to do that, you go like, oh Jesus, it took forever to build a machine learning model that just made a deterministic forecast. Now you're asking me to make a distributional forecast. Not only that, you want a joint distributional forecast. How am I going to do that? And yeah, I was alluding to that earlier. What you do is you shove your forecast that you're having. So you use your models, your training techniques with which you came up with the current models and cross-validate them, right? So say you do a 10-fold cross-validation. You use 90% of the training data to forecast the remaining 10. Now, on the remaining 10, you're going to get residuals, meaning there's a forecast of what this value was and what its actual value was, okay? And now if you do that, you get a whole vector for this if you have multiple things that you're forecasting at the same time, right? So for every training example, after you did this 10 times, every training example will have been in the validation set in the 10% once. So you're going to get residual vector for each one of those training examples that you had in your training set. You can do a covariance analysis on that, and that gives you a joint distribution on how these residuals are moving. And you can just use that in the solver in order to say, well, these are the scenarios that I'm predicting. Right? So you get a current prediction for what happens tomorrow, and you just sample from that covariance in order to generate scenarios around that mean that you predicted. All you need to do, it's really not that hard. It's I mean, from a software engineering standpoint, it's like 3 lines of Python for your machine learning team to build a joint distributional forecast for multiple things that you're estimating. And you're immediately going to get much, much more robust solutions that hold up in reality and don't just work for a scenario that never happens.
Thank you, Meinolf. That makes sense. I was going to say instead of ML team, I was going to say OR team, but hey, we're getting closer to one another.
Yeah. Well, I mean, obviously, if you're more sophisticated, many machine learning models, if you're actually making a multivariate forecast, they might already come with distributional forecasts, right? So then use them and just sample from those distributions, provide a sampling function for the solver, and you can use that directly. But if you don't have that and you just go like, oh man, yeah, but I have a way to forecast demand, but it doesn't give me a distribution. And I have a way to, I don't know, estimate electricity prices for tomorrow for every hour. And of course they go in unison, right? The hourly forecast of how much electricity is going to cost or what the demand is going to be is very, very much correlated. So if you're looking at that and you go like, I don't want to start from scratch building all that forecasting thing anymore, there are very simple workarounds there that are literally just 3 lines in Python. And since the exact probabilities don't matter anyway, you're still going to get vastly better solutions than if you're just taking the mean forecast and do a point estimate optimization on them.
Thank you.
Yep. Thanks for the question, Antonio.
Okay, probably I want to make not a question, but a comment. You just mentioned it's just 3 lines of Python code. And let's assume people who even know Python, when they look on your code and see such words as tensor, gamma, and hear these words first time in their life, and this is a little bit too much for them. And what are your plans to democratize your seeker to make it more available to regular people without operation research background?
I sense an LLM fan. Well, this is kind of where everybody is headed right now, right? Is to say, well, can't we just use LLMs to do that? I am deeply, since we're building this solver and we have to do things, I very frequently consult LLMs when we're coding. And the code that they're producing is so abysmal that I have severe doubts that we will get there anytime soon. So to answer your question, number one is there are, I think, 20,000 people coming out of our department, students who just learned all of this stuff this year alone. In the past 10 years, you have 200,000 analysts that you can fall back on. You can hire people like Tim, for example. who will do this kind of stuff for you, and they will do it right. And honestly, what Tim costs, you will recover in a month compared to what you can put together yourself. Number two, yes, sure, you can use helpers, but the other thing that we do is that we actually build verticals on top of the solver as we speak. So we already built an inventory optimization planner, so plenty, that you can just buy directly, and it essentially does multi-objective stochastic optimization for inventory. And there is no need for you to build any Python code or anything like that. But that will solve the problem for you. If you need that adjusted for your particular thing, you go back to Tim, right? And again, you will recover your costs very, very quickly. The last thing, of course, is what we're trying to do here is that we don't invent a new modeling language or something like this, right? This is all plain Python. It's very simple to learn, actually. We have tutorials, we do workshops in Seeker. You can basically just read what actually happens in your system here if you know Python. So any standard developer ought to be able in a position where they can stand up a solution like this. Not as good as Tim, but if you have somebody who knows Python, it is not a big lift to actually utilize the optimization software, even if you're not an OI expert.
Okay, so if I summarize what you said, there are always problems that requires the expert, and this is reality, and we should not pretend the LLM or just people without serious understanding of such things as stochastic optimization would be able to handle this, and this is fair assumptions, but I assume that the team just mentioned by you in his presentation will talk about bringing complex optimization and uncertainty to operational teams, and it would be more interesting to hear his answer during his presentation. And meanwhile, we have a question from Ralph.
Yeah.
Ralph? Yes, thank you. I've attended one of Meinolf's workshops that I've been getting some hands-on on Seeker. So I can speak like it's a very cool tool, right? So I'm new to OR. I'm on the data side, on the machine learning side, so I can speak. It's very interesting. You have to rewire the way you think stochastically, right? My question today is the following. So you can get familiar, right, with this new way of solving things. You can try it on your data, on the typical problems you have, right? And what you showed today is that's something I was planning to do. So just see how sensitive it is, right? So you're saying it's not sensitive. You change that distribution. It's not much sense. It's sensitive, like the data changes, but you're still getting better outcomes, right? You're getting better outcomes than the classical way. Now, let's say I do this for like a bunch of problems, change it. I feel confident about it. Now, the question is, how can I be sure if I have a new type of problems, right? How can I still be sure that the distribution is not sensitive? Like I'm kind of reluctant to accept, kind of way, to be safe, right? That the fact that, hey, it's not sensitive. Like I know it's not sensitive for the ones I tested, but how can I be sure, especially for somebody who didn't, right? If I go to my clients, right, they might want to test it and do that full analysis on like that sensitivity or not. So can you prove that? Is there a way to prove or to communicate that that performance gain versus the classical way in general, or does it always have to be case specific or problem specific?
So I mean, there's a very practical way on how you go about this, and that is you simply replace 3 lines here where you don't make this stochastic true, you make it false, and then just don't give it the gamma, just give it the actual times. So now you're going to get a deterministic solution to it. Right, so so you can use the exact same program to just get a deterministic solution, and then you can compare that under the stochasticity and see if you're doing better. That is like the unsatisfactory. Well, try it out on your problem answer, right? But there is a theoretical argument. Are you familiar with the thin shell theorem?
Yes, you mentioned that last time. Yes.
Yeah. So imagine that you have 100 normally distributed variables, right? So you have a mean and you have a standard deviation for all of them, and you have 100 of them. So now you're going to take a new scenario, well, what the optimization solver will go for, right? So deterministic optimization solver for is going to be the center of that shell, right? So the mean for everybody, right? But in reality, we know that the vast probability mass, if you sample independently 100 normal distributions, is going to be on a very, very thin shell that surrounds the median. This is where all the probability mass resides. It's here, and you optimize for that little point in the middle. You should have optimized for the sphere, for that shell, not for the point in the middle. And the reason that we're optimizing for
not the middle is good. So you're saying
it is not
as the middle, yes.
The likelihood that so if you sample 100 normally distributed scenarios, and you're going to be, so say with standard deviation 1, right? So the shell should have a length 10. If you're going to get something that is at least within 1 distance of the center, you would be 9 sigma out. so never happens. If you sample 100 normal variables, you won't be anywhere close to the center. You will be somewhere on the surface. And so, Jesus, I don't know where you're going to be on the surface, but what I'm asking you is find a solution that works on the surface and not one that works just in the center. And that's what we're doing. And the very fact that we're optimizing to optimality for the center makes us woefully overfit a scenario that will never, ever happen. It won't happen, not in your lifetime.
Yeah.
So that's a theoretical argument behind it. But in reality, you can always try it out. Very simple. It's just, it's just a few lines of code that you're changing.
Yes. So practically, you're recommending do the experiment you've done today, right? Like do it on your problem. Make sure that you're on that safe side of that line, right? And then once you're confident with that, when you go to production, forget about the deterministic and only run stochastic. Like do that kind of sanity check before. Yeah. Okay.
Yeah.
Okay. Thank you.
Okay, we have one more question. Safin, go ahead.
Hi, thank you. I planned for popcorn at 11, but Meinolf it was rescheduled at 9, so I don't have it with me. I know we want to be a provocative talk as usual, so it was very interesting. Thank you so much. So I didn't try Seeker yet, but it's on my to-do list. I'm very interested in what you are doing. But the mental model that I am having right now, and correct me if I'm wrong, is that you put your simulator inside your solver.
Yes.
But then there are other, and now you are comparing it to a deterministic approach where you run it once. What about putting the simulator outside the solver? Let's say you solve, you still have your distribution, the same as you did with your stochastic approach. So then you run with your first estimated values at once. Then you run your simulator with the same distribution that you used, and then you see the results, and then you adapt those hyperparameters in order to minimize the number of bumps. You did the same next time.
Yes. So I mean, this is something that we often hear Warren Powell propagate is to say, right? So he calls it like real life learning or something like this, right? So you start with some safety stock for your inventory, and then over time you're seeing how well your safety stock works, and then you just adjust it, right? So yeah, you can do it this way. The problem is you're assuming that over the time that you're learning, the system is stable, and it usually isn't. So, I mean, never mind that you have this huge cost. I mean, the errors that you're going to do in inventory will probably leave you with a lot of stranded inventory. That's number one. So it's not like you can go back to the original state there if you just simulate in real life. No can do. It will cost you dearly to actually do that. And what you're learning might no longer be applicable to the next season. Right. So if you do sunscreen inventory, well, season's over. So this is, you could try learn more next year. But it's right. So you see what I'm saying. It's like if you want to prepare for a future that you're forecasting, and that future is vague, as right, all forecasts are difficult, and so far as they regard the future, put a cloud on it. Right, come up with a plan that works against the whole cloud of things, the whole hurricane path funnel that you could be looking at, and not just the mean scenario there. It's very, very dangerous to do that. Yeah.
Would it be a
I have
fair
a whole
comparison
YouTube.
if you did, let's say in the future talk, would it be a fair comparison if you compared this both scenarios? Let's say you run it with a simulator outside, and then you compare both scenarios.
Look, so I mean, this is sometimes what people do, right? So they will say, I mean, especially like network design, for example, the company will come up with 10 scenarios of how their demand and their growth and whatnot could evolve. And then they compute an optimal network design for each one of those 10 scenarios. And then they have a heated debate which one of them to take. You don't need any of them. You don't want one that is optimized for one of your 10 scenarios. You want a compromise candidate that works against all of them.
Yeah, but that's why you come back and you choose the scenario. It's not you choose one scenario.
But you can't come back. I mean, look, if you build distribution centers, they cost a couple $1 million. So you know, once you decided to build in Oregon, you built in Oregon. Right? The world isn't always like, yeah, I can easily backtrack. If it is, you don't have much of a problem. If recourse doesn't cost anything, then don't do it stochastically, just do recourse. But the real world is costly if you're making wrong decisions. I have a whole YouTube video on the question of, you know, where the simulation should reside, and it's right. So I mean, you can try and put it into the machine learning. You can try and put it right when aggregating different solutions. The only reasonable way to do that is to put it into the solver. When you're deciding what is a good plan, you look at the variability that might hit you. That is how you evaluate how good your plan is, against the variability that might hit you, not outside.
Okay. Yeah. We're running almost out of time. Thank you.
Yes. We started
early. I just want to make a comment that Meinolf did a very smart thing. His presentation was short, but he specifically gave opportunity to our attendees to ask good questions. And while we have only 3 minutes left, I cannot resist temptation to ask another question from my practical experience in situations when, for example, I delivered some very sophisticated algorithm decision model to customers, and they ask question, Jacob, we trust you did very good job, but how can we trust that you implemented all constraints correctly? And how do we know this? And my answer was, let's run rule engine after, and we can validate what rules were satisfied or what constraints were satisfied, what were violated, and if they violated, how much they were violated. So what is your answer for your sophisticated algorithm would be?
So the Seeker 7, which is about to come out now in September, will have an assurance suite with it. So what you can do there is you can ask the thing to produce test sets for you, so that you just verify the model that you implemented, right? So you can do that. You can look at the joint distribution of multiple stochastic terms that you have in your model, whether they are actually coming from a distribution directly or somehow derived from there. So there's a whole suite that we're building around this, which is supposed to help developers verify that the model is correct. We're adding callbacks so that you can monitor during production and have your own escalation processes triggered if the solver runs into certain situations. So like that, you make it easier for somebody who actually has to run your model in production to find what the errors are and what to do when, right? So you can just use that stuff there. And we're also adding things like a new multi-objective optimizer that is supposed to help people who do one-off analyses. So not things that run in operation every day. But a question like, okay, so like network design, for example, where you kind of on an explorative path in terms of, well, what is the best bang for the buck that I can get for my different KPIs? So we are looking at three different personas there: the person who builds the model and has to verify it, the person who has to run the model and make sure it works while it's in production, and then somebody who's kind of in intermediate, right? So somebody who's developing the model to answer a strategic question, and that's our answer to the usability and verification around the solver. Our competitors call it explanations. I don't like that term at all. It was stolen from ML, and it's not explaining anything. It's just, it's giving you evidence that what you did was correct.
Okay, thank you very much, and
Thanks,
it was
Jacob.
a great presentation, and we need to move forward. Thank you, Meinolf. And
Thanks
you
a
can
bunch.
put some useful links in the chat.
Oh yes, I will do that.